Hello students, welcome to EPG Pathshala. I am Professor Devendra Mohan from Department of Physics, Guru Jambheshwar University of Science and Technology, Hisar in Haryana. Today we will talk on molecular orbital theory under the paper Atomic, Molecular and Laser Spectroscopy. After completing this module, we will be able to learn molecular orbital method, molecular orbital treatment of hydrogen molecule ion, molecular orbital theory for hydrogen molecule. Molecular orbital theory, in order to describe the electronic structure of molecules, two models have been deployed. The molecular orbital method developed by Mulliken, and the second is valence band method by Hitler and London. So molecular orbital method, molecular orbitals have the same sequence as the atomic orbitals, and also the molecular quantum numbers are associated with these orbitals in the same way. With a quantum mechanical approach, the molecular orbital are associated with molecular wave functions that describe molecular energy states that are then extended to include all the nuclei in it, and hence will be polycentric. However, the filling the orbital with system of electrons is done in accordance with Pauli's exclusion principle. Therefore, first construct reasonable molecular orbitals that can be done in number of ways. So molecular orbitals are taken as a function of atomic orbitals centered on the individual atoms, as molecules consist of atoms. The trivial approach for obtaining the molecular orbital is the linear combination of atomic orbitals. The molecular orbitals is written as a linear combination of the atomic orbitals as psi is equal to C1 psi 1 plus C2 psi 2 and so on. Psi I are individual atomic orbitals. The constant Ci are to be selected so that the energy given by psi is minimum, and further combining atomic orbitals must have energies of comparable magnitude, considerable overlapping and the same symmetry. The electron has tendency to remain most of the time in the lowest energy atomic orbital if the orbitals have different energies. Molecular orbital treatment of hydrogen molecular ion. Considering an electron of charge E associated with two nuclei A and B, each with positive charge separated by a distance r. The electron in the neighborhood of A is to be described by the atomic orbital psi A centered on A and by the atomic orbital psi B centered on B when it is in the neighborhood of B. Let us find firstly a set of molecular orbitals for the molecule so that it is close to psi A in the neighborhood of A and close to psi B in the neighborhood of B. As molecular orbital has to be a linear combination of psi A and psi B, therefore the wave function psi is written as equal to C1 psi A plus C2 psi B. C1 and C2 are constants to be selected so that the wave function psi corresponds to a minimum value of energy. Writing the Schrodinger equation and the energy E of the system, H psi is equal to E psi, where E is in matrix terms psi H psi upon psi psi. Psi A and psi B are 1s atomic orbitals given by psi A is equal to 1 upon pi under the root 1 upon A0 raised to the power 3 by 2 e raised to the power minus Ra upon A0, and psi B is equal to 1 upon pi under the root 1 upon A0 3 by 2 e raised to the power minus Ra upon A0. The Hamiltonian of the system is H is equal to minus h square upon 2m del square minus E square upon Ra minus E square upon Rb plus E square upon R. Now, m is the mass of the electron and the fourth term represents the electrostatic repulsion between the nuclei and the electron. So, E is equal to C1 psi A plus C2 psi B H C1 psi A plus C2 psi B upon C1 psi A plus C2 psi B C1 psi A plus C2 psi B. Normalizing the atomic orbital psi A and psi B, E is equal to C1 square psi A H psi A plus C1 star C2 psi A H psi B plus C2 star C1 psi B H psi A plus C2 star square psi B H psi B upon C1 square plus C2 square plus C1 star C2 psi A psi B plus C2 star C1 psi B psi A. Now, the integrals psi A H psi A is equal to H AA and psi B H psi B is equal to H BB. These are referred as the Coulomb integrals, while psi A H psi B is equal to H AB, psi B H psi A is equal to H BA. These are resonance or exchange integrals, and psi A psi B is equal to psi B upon psi A is equal to S, and these are referred to as the overlap integrals. HAA and HBB are the energies of the atomic orbitals psi A and psi B in the molecular skeleton, and HAB is equal to HBA star. According to the variational theorem, E greater than equal to E0 as a selection of the wave function is arbitrary. Here E0 is the exact ground state energy of the system. The energy E has to be minimized with respect to C1 and C2, taking HAA, HBB, HAB, HBA as constants. E becomes a function of C1 and C2, and considering the atomic orbital psi A and psi B to be real, that is E C1 square plus C2 square plus 2C1 C2 S is equal to C1 square HAA plus C2 square HBB plus 2C1 C2 HAB. And for the energy to be minimum, curly E upon curly C1 is equal to 0. So, E into 2C1 plus 2C2 S is equal to 2C1 HAA plus 2C2 HAB. Now, HAA minus E into C1 plus HAB minus ES into C2 is equal to 0, and using the condition curly E upon curly C2 is equal to 0, one gets HAB minus ES C1 plus HBB minus E C2 is equal to 0. And these simultaneous homogeneous equations in C1 and C2 have non-trivial solutions only if the determinant in the first row HAA minus E and HAB minus ES, and in the second row HAB minus ES, HBB minus E is equal to 0. This determinant, called the secular determinant, gives HAA minus E, HBB minus E minus HAB minus ES square is equal to 0, and the two roots for E are the allowed energy values of the system. Notice that for the homonuclear diatomic molecule like H2 ion, the nuclei A and B are identical. Therefore, HAA is equal to HBB, and therefore, the above equation is written as HAA minus E is equal to plus minus HAB minus ES, and this gives a two value of energy. One is E1 HAA plus HAB upon 1 plus S, and E2 is equal to HAA plus HAB upon 1 minus S. Combining these two equations as mentioned A and B, plus minus HAB minus ESC1 plus HAB minus ESC2 is equal to 0. And now from this equation, C1 is equal to C2 for energy E1 and C1 is equal to minus C2 for energy E2. So, the wave functions corresponding to energies E1 and E2 are respectively psi 1 is equal to C1 into psi A plus psi B, and psi 2 is equal to C2 into psi A minus psi B. And normalizing these, psi 1 is equal to psi A plus psi B upon 2 plus 2s under the root, and psi 2 is equal to psi A minus psi B upon 2 minus 2s under the root. The Coulomb integral is therefore HAA is equal to psi A minus h square upon 2m del square minus e square upon RA psi A minus psi A e square upon RB psi A plus psi A e square upon R psi A. The first term is simply the ground state energy of the hydrogen atom EH, since the operator in it is the hydrogen atom Hamiltonian and psi A is the one electron wave function. The nuclear repulsion term E square upon R is independent of the electronic coordinates. So, further VAA is equal to psi A e square upon RB psi A, and VAB is equal to psi A e square upon RB psi B. HAA is equal to EH minus VAA plus E square upon R, refer to equation C, and HAB is equal to EHS minus VAB plus E square upon RS, refer to as equation D. Now, the value of the quantities VAA, VBB, S and the nuclear repulsion energy E square upon R depend on the internuclear distance R and are always positive. If the two nuclei are infinitely separated, then overlap S is equal to 0 and S is equal to 1 if these are together. Equations C and D, one is able to write down E1 and E2. E1 is equal to EH minus VAA plus VAB upon 1 plus S plus E square upon R, and E2 is equal to EH plus minus VAA minus VAB upon 1 minus S plus E square upon R. And psi 1 corresponding to molecular orbital has energy E1 lower than that of the atomic orbitals from which it is formed, as is clear from the figure given over here. In case of psi 2, the energy E2 is higher than that of the atomic orbitals, and this figure depicts the relative energies of the molecular orbitals and their constituent atomic orbitals. The wave function psi 1 corresponds to the situation where there is a built up of electron density between the two nuclei and a more effective screening of one nucleus from the other. This suggests that a bond has been formed that is described by a bonding molecular orbital. The other possibility, psi 2, corresponds to the situation where there is a depletion of charge between the two nuclei and a larger nuclear repulsion that results in an anti-bonding orbital. Figure 3 depicts the formation of bonding and anti-bonding orbitals from two 1s atomic orbitals. Both these orbitals are symmetrical about the internuclear axis. Molecular orbitals that are symmetrical about the internuclear axis are designated by a sigma, and those which are not symmetrical about the internuclear axis are designated by pi. The figure gives us the bonding orbitals and the anti-bonding orbitals. The bonding orbitals are denoted by the symbol 1s sigma, as is produced from two 1s atomic orbitals. The anti-bonding state is given by the symbol 1s sigma star, where sigma star representing the higher energy, and the figure demonstrates the probability density for the bonding and anti-bonding states. The A part gives us the probability density functions. In case of the hydrogen molecule ion, the full lines represent psi 1 square or psi 2 square, while the broken lines represent psi A square and psi B square. And in the B part, contours of equal electrodensity have been depicted for psi 1 square and psi 2 square. Molecular orbital theory for hydrogen molecule. The treatment of hydrogen molecule in molecular orbital theory is essentially the same as that of hydrogen ion molecule. The Hamiltonian operator for hydrogen molecule is H is equal to minus h square upon 2m del 1 square minus e square upon Ra A1 minus e square upon Rb1 plus minus h square upon 2m del 2 square minus e square upon Rb2 minus e square upon Ra2 plus e square upon R12 plus e square upon R. The figure is self-explanatory, as 1 and 2 represent the electrons and A and B protons that has been represented in the figure. Writing Hi, where I will replace the electrons 1 and 2, is equal to minus h square upon 2m del 1 del I square minus e square upon R Ai minus e square upon Rbi. Now H is equal to H1 plus e square upon R plus H2 plus e square upon R plus e square upon R12 minus e square upon R. Now compute the expectation value of H with the trial wave function. It is noteworthy that the term minus e square upon R is independent of electronic coordinates. The Hamiltonian of the above equation is the same as the one solved for H2 ion molecule. Therefore, in the ground state of hydrogen molecule, both the electrons occupy the bonding orbital psi1 plus hydrogen ion, that is symmetric with respect to interchange of nuclei A and B, and therefore considering the trial wave function for the hydrogen molecule, psi mo is equal to psi1 1 psi1 2, and including the electron spin and Pauli principle into the formalism, spin functions for the two electron system are, for the case of symmetric, alpha 1 alpha 2 1 upon root 2 alpha 1 beta 2 plus beta 1 alpha 2 and beta 1 beta 2, and in case of antisymmetric, it is 1 upon root 2 alpha 1 beta 2 minus beta 1 alpha 2. Alpha 1 means the first electron is in a spin up state and beta 1 means the first electron is in a spin down state, and likewise alpha 2 means the first electron is in a spin down state and beta 1 means the first electron is in a spin up state. So as the Pauli's principle dictates that the total wave function must be antisymmetric with respect to the interchange of the two electrons. Therefore, the symmetric psi mo has to combine with the antisymmetric spin part to give the wave function psi 1 1 psi 1 2 1 upon root 2 alpha 1 beta 2 minus beta 1 alpha 2. This corresponds to a singlet state as its spin s is equal to 0. The energy is not affected by the inclusion of the spin part because the Hamiltonian does contain spin terms, and therefore the space part is to be considered for the MO for evaluation of energy. So using psi 1 is equal to C1 psi A plus psi B, psi 2 is equal to C2 psi A minus psi B, writing psi MO is equal to 1 upon 2 1 plus S psi A1 plus psi B1 psi A2 plus psi B2, and using the trial wave function psi MO H psi MO is equal to psi MO H1 plus E square upon R psi MO plus psi MO H2 plus E square upon R psi MO plus psi MO square upon R12 psi MO minus psi MO E square upon R psi MO. The above equation can also be written as psi MO is equal to 1 by 2 1 plus S psi A1 psi A2 plus psi A1 psi B2 plus psi A1 psi B2 plus psi B1 psi A2. The first two terms corresponds to the situation when both the electrons are associated with the same proton, and these represent the ionic structures Ha minus, Hb plus and Ha plus, Hb minus respectively. However, the third and fourth terms represent the situation where the electrons are shared equally by both the protons, and hence they correspond to covalent structures of the hydrogen molecule. What will be the spin functions for a system of two indistinguishable electrons? As the spin states of electrons labeled as 1 and 2, alpha 1, beta 1 and alpha 2, beta 2. Alpha 1 can combine with the functions of electron 2 in two ways, alpha 1 alpha 2 and alpha 1 beta 2. Similarly, beta 1 can combine with the functions of electron 2 in two ways, beta 1 alpha 2 and beta 1 beta 2. That means there are four basic product functions, sigma 1 sigma 2, sigma 1 beta 2, beta 1 sigma 2 and beta 1 beta 2. Obviously, the first and the last are symmetric with respect to an interchange of electrons 1 and 2. However, the second and third are neither symmetric nor antisymmetric, and by linear combination of the two, these can be made symmetric or antisymmetric. So, the following spin functions for a two electron system are symmetric, it is alpha 1 alpha 2, 1 upon root 2, alpha 1 beta 2 plus beta 1 alpha 2 and beta 1 beta 2, while for the case of antisymmetric, it is 1 by root 2, alpha 1 beta 2 minus beta 1 alpha 2, and the factor 1 by root 2 is the normalization constant. Now, in the next assignment, obtain the normalization psi 1 is equal to psi a plus psi b upon 2 plus 2s root and psi 2 is equal to psi a minus psi b upon 2 minus 2s root from psi 1 is equal to C1 psi a plus psi b and psi 2 is equal to C2 into psi a minus psi b, and also tell the normalization factor if the two nuclei are at infinite distance. Now, as psi 1 is equal to C1 into psi a plus psi b, psi 2 is equal to C2 into psi a minus psi b, and normalization of psi 1 gives us C1 square psi a plus psi b psi a plus psi b is equal to 1, C1 square psi a plus psi b plus psi b plus psi b psi a is equal to 1. C1 square 1 plus 1 plus s is equal to 1. One is able to write down C1 is equal to 1 upon 2 plus 2s under the root and psi 1 is equal to psi a plus psi b upon 2 plus 2s under the root. Similarly, normalization of psi 2 gives C2 square psi a plus psi b minus psi b minus psi b psi a is equal to 1. So, C2 is equal to 1 upon 2 minus 2s under the root and psi 2 is equal to psi a minus psi b upon 2 minus 2s under the root. And if the two nuclei are at a infinite distance, the overlap integral is 0, that means psi a psi b is equal to psi b psi a is equal to 0, and normalization factor for both psi 1 and psi 2 is root 2. Molecular orbital theory. In order to describe the electronic structure of molecules, two models have been deployed. The molecular orbital method developed by Mulliken, and the second is valence band method by Hitler and London. So, molecular orbital method, molecular orbitals have the same sequence as the atomic orbitals, and also the molecular quantum numbers are associated with these orbitals in the same way. With a quantum mechanical approach, the molecular orbital are associated with molecular wave functions that describe molecular energy states that are then extended to include all the nuclei in it and hence will be polycentric. However, the filling the orbital with system of electrons is done in accordance with Pauli's exclusion principle. Therefore, first construct reasonable molecular orbitals that can be done in number of ways. So, molecular orbitals are taken as a function of atomic orbitals centered on the individual atoms, as molecules consist of atoms. The trivial approach for obtaining the molecular orbital is the linear combination of atomic orbitals. The molecular orbitals is written as a linear combination of the atomic orbitals as psi is equal to C1 psi 1 plus C2 psi 2 and so on. Psi I are individual atomic orbitals. The constant Ci are to be selected so that the energy given by psi is minimum, and further combining atomic orbitals must have energies of comparable magnitude, considerable overlapping and the same symmetry. The electron has tendency to remain most of the time in the lowest energy atomic orbital if the orbitals have different energies.